Hello, welcome again to yet another video of Axiomatic Thermodynamics, and today we'll be talking about the second law of thermodynamics, which is pretty important in the field of axiomatic thermodynamics because it also gives rise to two very important factors in thermodynamics, which are the definition of absolute zero for temperature and the definition of entropy. So we can already start by saying that the second law of thermodynamics is described in different ways in different books. However, most of the statements which are made come from two scientists, two physicists who were really famous in their fields, and especially in thermodynamics. And they mostly have equivalent statements, because the negation of one of those statements is also the negation of the other. So these two scientists are Rudolf Clausius, a Polish-born German physicist, and Lord Kelvin, as we know from the Kelvin scale of temperature. So William Thomson, his real name. Right, and we are going to show first the two statements of these two physicists, which actually culminate in the second law of thermodynamics. So we begin with the first statement, which is from Rudolf Clausius, who gave this statement in 1854 as he was in Berlin as a professor. And he says that there is no thermodynamic change where the sole objective or action of this change, the sole objective, it lies in the extraction of heat from a colder system and deposition of that heat to a hotter system. Right, and what would that mean for us? For us, it would basically mean that if we have a system whereby, let's say, a system A and a system B, whereby let's say that the system A is colder, so it's with blue color, and system B is hotter. So we would, from our daily experience, guess that maybe heat would flow from B to A. But we can also construct a machine that basically takes the heat from A and makes it even colder and deposits the heat in the heat reservoir, which is B. And this machine, it cannot be constructed in a way that it acts on its own without any exterior influence. So for example, if this machine has to transfer heat from A to B, there has to be some kind of work that has to be done by somebody from outside, so that it has the necessary capacity to transfer heat from A to B, because it is really against how the gradient of temperature works, because we know that heat flow would always happen from a hotter to a colder system. Why it is that? Why do systems try to reach a thermal balance, a thermal equilibrium? That has again its reasons in typicality, which is a theory that comes in statistical physics. But when it was the time of axiomatic thermodynamics, it was proposed as an axiom, stating that the heat flow basically happens from hotter to colder systems. And if you want to do something against this heat flow, then you would need a machine whereby you have to do some kind of work on the machine in order for it to have a capacity to do this. It cannot work on its own. Like, it cannot be its sole action or objective. Right. The second statement, by the way, both these pictures are from Wikipedia. Right, just to give clarification that those are not pictures taken by me. I'm not that old. And right, about the second statement, which was given by William Thomson, who was the first Baron of Kelvin, and that is also the reason why he's called Lord Kelvin. He says that it is impossible to construct a periodically working machine whereby it does nothing other than cooling of a heat reservoir or some form of mechanical work. So what it means is that there cannot be a machine that can be built that works periodically for infinite times, forever, on its own, without any kind of external influence. So it is impossible to construct such a working machine, and we call these kinds of working machines perpetual machines. You have probably seen in many popular science videos that perpetual machines have mostly like double or triple pendulums, whereby they continuously move. They have their pendulum movements. But Lord Kelvin says that such perpetual machines are not possible. Why the double pendulum still works, we will be not going into that because then it will be a video of its own. But in thermodynamics, such a perpetual machine of first class, of first grade, is not possible through the second law of thermodynamics. Right, and again, as I said, the two statements are then equivalent because the negation of Lord Kelvin's statement would also mean the negation of Clausius' statement. Right, and also very important, something that is also named after Lord Kelvin is the scale of absolute temperature. What you see here is not OK, rather 0 Kelvin. One doesn't give degrees to Kelvin because I don't know. I do not really know the reason why degrees are not given. I would love to know it in the comments if anybody who is viewing the video knows it, but sadly I have never found any kind of reasoning given in any book. But yeah, so the absolute zero was defined using the triple point of nitrogen, of water, and the absolute zero was then defined using the triple point of water, and it is defined as then minus 273.1515 degrees Kelvin. Here should actually be a point, right? So that's why whenever we have x Kelvin of temperature, we basically add 273.15 to it to make it degree centigrade. Right. And now coming to the very important part of entropy. As we did a short detour into Carnot process in one of the earlier videos, we saw that there was this very weird pattern that emerged, whereby we saw that Q, the heat given to the system or taken out of the system, is not a state parameter or a state variable, but T is. And this ratio is then somehow a weird ratio of a parameter which is not a state parameter and a parameter which is a state parameter. So Clausius, the guy from before, he actually saw this pattern and he defined this term as the entropy. And he stated that, okay, we have a non-state parameter and a state divided by a state parameter. So what he did was he divided both of them and he defined it as a state parameter, the entropy. And now he says that then entropy will also be conserved in reversible processes. Like in reversible processes, the change of entropy will basically be the change, the difference of entropy between 2 points. So let's say we have process whereby it moves from A to B in this way, and then basically the change of entropy, this is the wrong one, this one, the change of entropy will be the difference of entropy in the 2 points, and this can again obviously be done in the integral way, and this formula can then also be used for calculating the change in entropy. And this is but only possible with reversible processes. If we have any other process, it will actually be a greater equals of the change of entropy. And this is something also that the second law of thermodynamics kind of guarantees us. That is that the total entropy, which is basically the summation of the entropy change of a system with the entropy change of the environment, should either be 0 or greater than 0. So it always rises. So in a closed system, the entropy will always rise, and there's no reason as to why the entropy will decrease with time. The reason for this is also hidden in statistical physics, but it is in axiomatic thermodynamics, it is taken more of as an axiom. Right, I hope this video helped you. Entropy will be a very, very important topic in coming videos also, and in statistical physics we'll see how big of a role it plays. It basically defines, it describes why systems move into thermal equilibrium. Right, and I hope you like the video, as I said before, and please do press the like button and share it with your friends if you found it helpful. Comment any kind of constructive criticism that you have about the videos, what I can change about the videos and what I should add. And we'll meet again in another video sometime in the future. Thank you again.